Hello, my name is Andrei Poenaru. I'm a PhD student with the HPC group at Bristol in the UK, and I'm going to present to you a summary of our recent studies on using SVE for scientific computation. My work is around modern and future architectures for HPC, and a lot of it has been focused on the Arm Scalable Vector Extension, or SVE. At Bristol, we have been using ARM supercomputers every day since our Isambard system was installed in 2017. Isambard uses Marvell ThunderX2 processors, and it has recently received an update to double its size and add another partition using Fujitsu A64FX processors. We've also been studying SVE since it was announced a few years ago. Even though no hardware was available until very recently, using simulators and emulators, we worked directly with ARM and vendors building ARM-based systems to find and fix issues with early versions of the toolchains. This has led to stable and performant toolchains from the very first release versions. SVE is now in use in the latest generations of ARM-based HPC processors, as found in the A64FX chips in the Fugaku system in Japan and in our own Isambard 2. One of the interesting aspects of SVE is that it presents a novel research problem. Because vector length isn't fixed, but rather each implementation can choose its own, how do we choose the best vector length for future hardware? We've been looking at this from two perspectives. One, how well can applications take advantage of SVE at various vector lengths? And two, how does this choice interact with choices made in designing other parts of the chips? To address these questions, we've picked a number of mini-apps, each representative of a common class of HPC applications. BUDE is a molecular docking mini-app. CloverLeaf is a structure grid fluid dynamics application. MegaSweep is a memory bandwidth benchmark based on Snap, originally developed to investigate caching-related effects. And MiniFMM is a C++ task-based implementation of the fast multipole method. We ran instrumented versions of these applications on a single emulated SVE core, and we ignored anything outside the core computation. The inputs were scaled down such that we kept the same performance characteristics of real-world runs. The two main tools we use for our studies are the ARM Instruction Emulator, or ARMI, and an in-house cache simulator. ARMI emulates SVE programs on regular ARM v8 hardware and allows user-defined instrumentation code to collect data about the running program at the same time. It can also be used to generate memory traces, which can then be fed to a cache simulator. Our cache simulator was developed from scratch, and in validation it showed less than 10% error versus hardware counter data collected from real ThunderX2 and A64FX chips. The first step in our analysis was to investigate how the applications vectorized, both on SVE and on the other current generation vector platforms. We selected the main computation loops from the applications and looked at the compiler's ability to vectorize them in the three main HPC compilers, GCC, Cray, and ARM and Intel on the respective platforms. Each of the applications is presented as a row in this table. Immediately to the right, we list the number of core loops analyzed and their percentage of runtime on a real core of ThunderX2. Then, the compiler's performance, in terms of number of loops vectorized, is clustered by platforms. First is SVE, then Neon, the previous generation vector instruction set from ARM, and the one that ThunderX2 uses, then AVX. The results were the same for both AVX2 and AVX512, so they are shown as a single cluster in this table. Each cell is color-coded according to the percentage of loops vectorized. While the Intel compiler vectorized the highest number of loops on x86 platforms, the compilers which can run on all the platforms studied, GCC and Cray, vectorized at least as many loops on SVE as they did on Neon and AVX, and sometimes even more. This supports SVE as an instruction set that is well suited for scientific compute. Please note that the Cray results are obtained from a pre-release version of the Cray compiler for SVE. We then took each application and looked at the dynamic count of instructions executed using custom instrumentation through the ARM Instruction Emulator. This graph shows the instruction usage data for BUDE, the molecular dynamics mini-app. The leftmost cluster shows the data for a run in which vectorization is explicitly disabled. The next one shows data for a Neon target, such as the ThunderX2, and the remaining clusters each correspond to a selected SVE vector width, which can be given as a parameter to the emulator. Within each cluster, the colors correspond to different types of instructions. The light green is scalar ARMv8 operations, the orange is Neon, and the other colors are all different classes of SVE instructions. BUDE is a compute-bound application which makes good use of vectorization, so the number of executed instructions decreased as the vector length was increased, because each single instruction processed increasingly more data. CloverLeaf, the fluid dynamics mini-app, showed a different profile. First, not all of the code is vector code, so a significant portion of scalar instructions are executed even at wide SVE lengths. Most of the scalar code is from outer loops in loop nests, because the compiler only vectorized the innermost loops. Second, while all three compilers showed similar behavior at narrow widths, the number of instructions executed by the version compiled with Cray decreased much faster with vector length, suggesting better vectorization. With the Cray compiler, the number of scalar instructions also decreased with vector length, which may seem counterintuitive but can be explained by looking at how these compilers vectorize loops. Arm and GCC generate vector length agnostic code that can run on any vector width, but with Cray, the width needs to be set at compile time. With this information available, the Cray compiler generated scalar instructions for most of the loop control flow as opposed to SVE instructions. But the number of times these were executed still depended on how much data each vector instruction processed, thus resulting in a correlation of scalar instruction count with SVE width. For most of the mini-apps, regardless of what percentage of runtime was spent in vector code, when vector instructions were executed, the vector registers were fully filled. But in SVE, each instruction is predicated per lane, so it is possible to run vector instructions where any number of elements are masked out. In the worst case, this can mean executing vector instructions that only process a single useful element, thus gaining no benefit from this suboptimal vectorization over scalar code. We observed this effect to various extents in MiniFMM. Looking at the dynamic instruction count for MiniFMM provided a first hint at the issue. Vectorization does decrease the total instruction count up to 512 bits, but using larger vectors brings little benefit. Vector code is still being run at all lengths, but the number of instructions was very similar at 1024 and 2048 bits compared to 512 bits. This happened because even though wider registers were available, they were not being filled with useful data, and many of the lanes were masked out. This graph shows a histogram of the number of bits active in vector operations, grouped in 128 wide bins. A higher bar means more accesses had a number of bits active that falls in that bin. In each column, the last bar shows the percentage of operation in which all the lanes were active. When the vector registers are 128 bits wide, for example, the only way for an access to have between 128 and 255 bits active is for it to have exactly 128 bits active. Data is not shown for the Cray compiler because MiniFMM's build system does not support Cray. We can see that up to 512 bits, most of the accesses use the full vector width available. However, at 512 bits, already only a little over half the accesses use the full width, as opposed to more than 80% at the 128 bits. Going up to 1024 bits, some operations use more than 512 bits, but very few utilize the full 1024 available. At 2048 bits, the histogram is virtually identical to the 1024 one, because the additional vector width is not utilized. This MiniFMM example highlights that with SVE, because of the per lane predication, it is not enough to check that vector instructions are being run when analyzing performance, because it is possible for those operations to only use a small portion of the throughput available. Using our cache simulator, we looked at the effects on cache of these applications. We tested hypothetical cache configurations in which we varied the sizes of cache lines and the associativity of the cache. The values we tested include those commonly used today, but also smaller and larger options. In general, we found that increasing the line size helped in many cases. On the other hand, increasing the associativity didn't always help on its own. At large values, it was only more efficient if coupled with long lines. These heat maps show cache miss rates in percentages for CloverLeaf. Lower numbers are generally better and lighter colors correspond to those. The experiments were done on two levels of private cache. Level 1 is shown on the left and level 2 is shown on the right. The x-axis gives the associativity or set size in number of lines, and the y-axis gives the line size in bytes. CloverLeaf is memory bandwidth bound and roughly follows the profile of stream. A good portion of the access patterns are sequential, so this application benefited from larger cache lines, because a single load will bring in more elements to compute on. The set size did not have a big impact, except at the highest line size, 2048 bytes, where the extra associativity helped reduce evictions from arrays with longer stride access. Increasing associativity brought a bigger benefit when accesses were less structured. The biggest improvement for CloverLeaf from using bigger sets was 3.4 times fewer misses, whereas for MiniFMM it was 18.3 times, both at 2048 byte lines. This slide shows similar heat maps with miss rates for MegaSweep and MiniFMM, both at level 1. We also observed an interaction between the line size and the set size when using longer lines. At low associativity, for example 2 or 4-way, the number of misses was an order of magnitude higher than at high associativity. The paper goes into more details about the effects of these parameters on the mini-apps, including how they change when changing SVE widths. Using the cache simulator, we tracked how long data stays in cache before being evicted. We took the cache configurations used in the ThunderX2 and the A64FX and collected an empirical equivalent of the evict distance across a range of SVE vector widths. In general, we found that the cache setup used in the A64FX allowed more reuse, mostly due to its longer lines and larger total size. As the vector length was increased, the difference between the two cache configurations became more visible. These graphs show normalized histograms of the cache lifetimes for CloverLeaf. Each column corresponds to an SVE vector width, and each row is one of the cache configurations. The x-axis of each histogram gives the number of cycles spent in cache, and a taller bar means that more of the lines loaded had the lifetimes that falls into that bin. The more shifted to the right the curve is, the more reuse was achieved. The distribution of lifetimes showed two distinct peaks on the ThunderX2 configuration. CloverLeaf implements a multi-dimensional stencil algorithm, and so the rightmost peak corresponds to the higher cache friendliness of the inner dimensions of the data structure. At higher SVE widths, each vector memory axis touches more data, so data was evicted from cache sooner, shifting the curve to the left. These effects were not observed in the A64FX configuration, where the higher line size and total size allowed more of the outer dimensions to persist in cache, leading to more homogeneous cache usage overall. In the case of MegaSweep, the curve was narrower on the ThunderX2 configuration. There is a second peak here as well, but it is less distinct than in the case of CloverLeaf, and it is located to the left of the main peak. This corresponds to poor utilization of cache seen when running MegaSweep on real ThunderX2 hardware. On the A64FX configuration, the effect was not observed, even though this configuration has smaller associativity, thus further reinforcing the lack of a correlation between set size and cache performance at small and medium line sizes. These graphs only show data for the first level of cache, because level 2 results are harder to visualize. The differences between the two configurations are bigger, but the conclusions drawn are the same. Finally, this graph shows how the two cache configurations handled non-contiguous memory accesses. For each SVE vector length on the y-axis, a distribution of the number of lines touched is shown. A thicker bar means that a larger portion of all non-contiguous access is needed than many cache lines to be serviced. This is important because the performance of non-contiguous memory operations, that is, scatters and gathers, often depends on the number of cache lines touched. The larger cache lines of the A64FX allowed it to service requests using up to 3 times fewer cache lines when the SVE length was 1024 bits or higher. However, some requests were always spread far enough apart that they always needed more than a single cache line to be serviced. Throughout these studies, we recognized the need for a specific architecture research tool, a flexible, accurate, and fast simulation toolkit designed to simulate full HPC systems on HPC systems. We've been working on such a project for about 2 years now, and we call it SimEng. Its first goal is microarchitecture design space exploration centered around SVE, with further extensions planned to support the other common HPC architectures. We hope to be able to share a pre-release version of SimEng in mid-2021. To sum up, I have presented how real-world HPC applications can take advantage of the new features in SVE, as well as the challenges they face in doing so. Vectorization has become more important than ever, both at the source code level and in compiler toolchains, being virtually a requirement for good performance. However, the shift towards wider vectors brings additional considerations when designing hardware, and they are ever more important for future generations of hardware. The only way to make the right decisions for both system manufacturers and their users is through continued co-design and design space exploration, which is one of the greatest strengths of the ARM ecosystem in HPC. These are the 2 papers from which I extracted the results presented today. They show additional results and go into more detail on the effects observed, so I encourage you to read them if you are interested in any of our experiments. These links point to the Bristol HPC Group's GitHub pages, where you'll find reproducibility data for the papers, our up-to-date benchmarking scripts and results, and details about our other current work. Thank you for watching.